Welcome everybody to week 7. So this week is going to be about zk security. So we're going to be hearing from John Stevens, who is the CTO at Veridise, and he's going to be talking to us about smart contract security considerations today. So John, go ahead and take it away.
Hi, I'm actually the CEO now, but that's okay. I was the CTO for a while. Anyway, so yeah, I am the CEO of Veridise. We specialize in blockchain security, and in particular, we've been doing a lot of work on zk security. However, today I'm going to be going over kind of a high level of smart contract security, and tomorrow I believe I'm going to be going over zk security. So the talk today is going to focus more on breadth of smart contract security, and it's going to focus on types of issues, and then later, hopefully, we'll get into a little bit of how you can avoid them and techniques that you can use to hopefully try to find bugs yourself, either because you don't want to rely on a security audit to find all of the bugs, or just so you're aware of things that security auditors can and really should be doing. So let's get started. So the first thing that we're going to talk about is the smart contract security model. And what I mean by this is we're first going to go over a little bit about what a blockchain is, even though you guys know that, just so we're all on the same page about the threat model that you have when it that a smart contract typically has. So let's start with that. And so here is kind of your typical blockchain model. And what I mean by that is typically the way that we view blockchains is you've got a group of people who are allowed to execute transactions on a particular blockchain. And typically the way that they do that in blockchains that allow smart contracts is you've got code which is hosted somewhere on the blockchain, and that code ends up controlling the storage associated with that contract, which is, essentially the blockchain ledger that we end up having. And so you have users interacting with contracts, and those contracts in turn will interact with the ledger. You can have cases where users interact with the ledger directly, but because this is smart contract security, we're mostly just going to ignore that. So the thing that we need to be aware of, though, is that this model is a little bit more complicated, just because you have smart contracts that are going to be interacting with each other, and you need to be aware of the fact that an individual smart contract is going to control its own storage. And so even in cases where you have storage that can be owned by other contracts or users, something similar to Move as an example, you still have the smart contract defining the logic which controls how storage is updated or modified. And so for this reason, really, when we look at this execution model, we need to be a little bit more granular, where we consider individual contracts that can interact with each other, and also with storage, where each smart contract is the thing that's controlling its own storage on the blockchain. So in particular, there's a couple of assumptions that we can make based on this model. So the first assumption that we can make is that the execution is bounded. So all blockchains have some sort of a notion similar to gas, which is going to bound the execution. This makes sure that someone can't, maliciously execute an infinite transaction, and as a result bring down the entire chain. So a smart contract, or a transaction that executes a smart contract, is going to have to end at some point. In addition, because of the way that the blockchain is set up, we also kind of have this modular environment. And what I mean by that is you have individual smart contracts that define their own logic, and your contract can interact with other contracts, and they don't necessarily need to know specifics about each other. Instead, they can be launched after your contract, and your contract can be adjusted in order to interact with it. And so there's this modularity element to blockchains as well. And then finally, I already brought this up before, but the storage for a particular contract is managed by its own code, which means you can't have something like another contract maliciously updating the storage of another contract. If it is updating the storage of another contract, it's because that contract somehow gives it permission to do so, either by providing some sort of set API or something like that, which is unguarded and typically a bad idea. So this is where we get to the threat model. And so what I mean by a threat model is we have to understand where external actors are able to provide some sort of malicious input or malicious interaction with your contract. So there are two particular cases that we have to be concerned about when it comes to smart contract security. So one, because anyone is allowed to interact with a smart contract, pretty much, you can assume that at least some of the audience is going to be malicious. And so you can have malicious interactions from users where they might do something like try to call an API in a weird way in order to extract some benefit. In addition to that, because of the modularity of the ecosystem, you can also have people deploy malicious smart contracts, which you can interact with during the course of regular execution. So this could be because you allow users to specify a contract to call, or if somehow a value gets accidentally set to call a malicious contract. And so you have to be aware of who the malicious actors are when you are interacting with, the blockchain environment in general. So this kind of comes to the security considerations that we need to worry about. So one, I've already talked about, is adversarial users. The other one, which is the adversarial contracts, I call adversarial environment here because you don't necessarily know which contracts you interact with are going to be malicious or not. And then finally, the other thing that is worth knowing is some of the benefits that you get when working with a blockchain ecosystem that has static dispatch versus dynamic dispatch. And what I mean by that is dynamic dispatch means that your contract is allowed to essentially transfer control anywhere. It's not necessarily defined within your blockchain logic. In Solidity, as an example, you can essentially decide to call any particular address without knowing exactly what is going to be at the end of that call. Other blockchain ecosystems, though, have something called static dispatch, where essentially it requires you to have knowledge of who you're transferring control to. So this is anyone who's familiar with Move or something like that. They use a mechanism called static dispatch, where part of the information about control transfers is encoded when you end up compiling your contract, because you have to define statically the contracts at specific addresses that you are going to interact with. And so the reason why I bring this up is because static dispatch or ecosystems that use static dispatch end up being a little bit safer, because then you don't have to worry about things like reentrancies typically, whereas dynamic dispatch means you can do pretty much anything, and users can also try to use information or use that dynamic dispatch in order to perform malicious actions. So for those of you who are familiar with mechanisms like transaction.origin, the reason why that's a bad thing to use in Solidity is because of this dynamic dispatch, where someone can try to, essentially take over control of a transaction in order to gain some benefit. And so in that case, any permissions that you provide using transaction.origin could possibly be, overcome by essentially hijacking control of a particular transaction. And so it's also important to be aware of the type of ecosystem that you're operating in when considering the logic of the smart contract. Anyway, this kind of sets the threat model that we have in the smart contract ecosystem. And so I'll try to use this threat model in order to show how particular vulnerabilities occur in a typical environment. And here by typical, I mean, you can assume that we're operating in a blockchain like Solidity, where you have dynamic dispatch, and most of the examples that I'm going to give, or all of the examples that I'm going to give, are written in Solidity as well. Okay, so let's start with the easy one, the one that's the most well known. So here, what we're going to first start with is common vulnerabilities, like it said in the last slide. And so I'm going to go over some common vulnerabilities, which are useful to be aware of. And some of them you probably already know, but I'm going to kind of review what each common vulnerability or the cause of each common vulnerability at a high level, so that, you know, when you think of these common vulnerabilities, hopefully you're not thinking about it related to a specific piece of code. And so what I mean by that is there are many different types of reentrancies. So you've got the typical reentrancy where you make an external call and someone calls back into you. But then you also have these other reentrancies like cross-contract reentrancies and read-only reentrancies, which are very similar when you look at them from a high level, but they're, you know, different when you look at the specific use case. So with a reentrancy, basically what happens is you have a smart contract. Someone calls into that smart contract. It could be a user. It could be another contract. And then at some point, control exits your contract or your protocol. And then eventually some malicious protocol, or it doesn't really even have to be malicious, but some contract makes a call back into your protocol. And the problem here is if your protocol was left in a state that should be considered invalid, so let's say balances weren't updated or something like that, then some, you know, malicious action might be able to be taken, or some, you know, incorrect information might be retrieved. And so that's really what a reentrancy boils down to, is control is going to exit your contract or protocol while they are in an invalid state. So that means any state that is accessed might be invalid, or any state that's retrieved might not be reflective of the protocol as a whole. And so you really need to think about at any time that transfer or that control transfers out of your contract or set of contracts, you know, what the state of your protocol is, and make sure that it's not in a state that anyone calling back into it could take advantage of. And note that this isn't something that can necessarily be solved by like reentrancy guards, because reentrancy guards will protect a single contract. However, we have seen cases where there are cross-contract reentrancies because a single contract was left in a bad state, and as a result, you know, a reentrancy guard wouldn't help protect you. So even if you are using reentrancy guards, it's still useful to think about the state of your contracts and make sure that if one contract is in a bad state, it doesn't mean that all of the contracts are in, you know, a bad state. So let's take a look at an example where a reentrancy caused some, you know, theft. So most of you likely have heard of the DAO hack, and most of you likely know that the DAO hack happened because of a reentrancy. And this was one of the, you know, first cases of a very bad theft due to a reentrancy. And so, you know, the reentrancy here is fairly straightforward, but again, remember that this is only a single instance, and there are more complex instances of reentrancy attacks. So in the specific case of the DAO hack, what happened is they had a particular function called split DAO, and split DAO would eventually, you know, it basically was trying to split a DAO into two. And so it would do things like, you know, if someone had rewards on a single DAO, it would try to withdraw those rewards from them and provide them to the user. However, when they did so, you can see right here, they end up calling withdraw for, which in turn eventually calls this payout function on top. And that payout function uses a low-level call in order to transfer value to a particular user. And because at that particular state, none of the balances of the user had been adjusted, you can see that there is going to be this negative impact where, you know, someone can call split DAO again or something like that. And as a result of calling split DAO another time, they can again withdraw the same amount. And that's because the balances of that particular value has not been adjusted to zero. And so from the perspective of the smart contract, someone or that particular user still has a balance. So in this case, there are several ways to avoid it. Most of you have probably heard of, I don't remember what the name of the design pattern is right now. It's, yeah, off the top of my head, I don't remember the name of the design pattern, but either way, really what they should have done is they should have adjusted all of their state before transferring control externally in order to ensure that this contract was not left in, this particular state, because, obviously it was vulnerable, and this led to a very significant loss of funds. So the next case that we're going to look at is access control violations. And so what happens with an access control violation is you've got users who are interacting with your smart contract, and your smart contract might expect to have a particular, might expect some particular API to only be interacted with by specific users. And however, there is a way for some users to, overcome those checks in some way. So this is either because those checks were not properly performed, or because there was a way for someone to basically escalate their privileges in order to overcome those checks. And so really what an access control violation is when an unexpected entity is able to invoke some privileged functionality when you do not intend them to do so. So we can take a look here at a fairly famous case where this happens. So for those of you who aren't familiar, this is going to be the first parity wallet bug that we look at, because they had two in very quick succession. But basically what happened with the parity wallet is they were a fairly popular wallet a couple of years ago. And essentially the way that they set up their wallet is similar to many upgradable functions that are used nowadays. They had a wallet, which was essentially just a proxy, and it would call an implementation contract, which was this wallet library. And so essentially what the wallet library did is it set the implementation that was going to be used, or the method that people would interact with the contracts, and the wallet itself was essentially just, this fallback function, which would invoke the functionality in the library using a delegate call. And for those of you who aren't familiar, a delegate call is going to essentially allow another piece of code to interact within the storage space of the caller. And so what ends up happening in this particular case is there is this delegate call, which happens here, which is going to call into the library. And that delegate call allows anyone to make any particular call to the wallet library implementation, including to the initialize wallet function. Sorry, I thought there was another transition there. But the initialize wallet function is then going to update the owners, which meant someone could, initiate the init wallet function at any time in order to essentially steal control of a wallet. So obviously this is not very good, and it essentially allowed someone to overcome the access controls that were intended for the initialize wallet function, which was supposed to be called once and that's it, in order to gain access over the wallet and then steal all of the funds that were deposited within that wallet. Okay, the next case that we're going to look at is data validation errors. And so a data validation error is going to be similar to an access control error in that it allows someone to call a function with an unexpected value. And what I mean by that is someone can call a function with a value that, maybe the contract was not intended to take in. However, the controls on the values that users could pass in were not implemented correctly, or were not enforced. So in this particular case, a data validation error is one where a function accepts values that can trigger some undefined behavior. So if you look at the example that I have on the slide, a malicious user might be able to call withdraw with some amount greater than their balance, and if the contract is not actually checked to make sure that the value is within the bounds of their balance, then obviously that's going to be a data valuation or validation error. So we can take a look at a fairly famous case where this data validation error ended up causing a fairly significant problem. And So this is the Nomad bridge hack. And for those of you who aren't familiar with how this happened, essentially you had this initialize function which would set some confirmed root. So it doesn't really matter for the case of this presentation what that confirmed root is, but the important thing is here the confirmed root would essentially say whether or not someone had permission to do something. And so if confirmed at was 1, then that meant that someone was able to do something, whereas if it was 0, they weren't. And so the problem happened because the admins of Nomad ended up setting the confirmed root to 0. And as a result, when anyone called processed, what would happen is this acceptable roots function would be called. And acceptable roots would end up checking confirmed at. However, what you can see is that the input to acceptable roots was this messages with message hash. And the problem that you end up having here is because all mappings end up defaulting to 0 if they don't have a particular value. If someone passed in a message hash that didn't exist, then messages would return 0, and 0 ended up being a confirmed root. So as a result, the Nomad bridge ended up allowing anyone to process a message that had not been seen before. And this all happened because the admins did not check to make sure that committed root was 0. It should also be noted that in the Nomad audit, I'm fairly certain I'm remembering this correctly, but this was something that the auditors pointed out that Nomad decided to just acknowledge because, they wouldn't pass in, an invalid value at initialization, but it ended up happening anyway. So it is always important, even in cases where you think, we're the ones who are going to be making this call, we aren't going to make mistakes when invoking it, to still include that validation, because the Nomad bridge hack ended up, losing millions of dollars worth of funds for users just because invalid messages could be processed due to this one small mistake. Okay, so the next case that we're going to look at is a denial of service. So for those of you who aren't familiar with it, basically what a denial of service is going to do is, a user is going to be able to execute a particular function. So here you see a user being able to execute something called draw. But a denial of service occurs when you have another user who's able to invoke a particular function that impacts the result of another user, or impacts the ability of another user to take a particular action. And so in particular, this is, if it's not desired, because there, are certainly cases where someone like an admin should be able to do things like lock a contract, which shouldn't be considered as a denial of service. So this is particularly cases that the protocol does not intend. So a denial of service can be defined as a case where a user's interaction can unexpectedly deny service to another user. So we can take a look at a fairly famous case where this happens. And again, we're going to look at another parity hack. So for those of you who aren't familiar with parity, essentially what happened was the previous attack that we saw before ended up hitting parity, and then they went and they fixed it. However, their fix ended up introducing another vulnerability, or it kind of exposed another vulnerability a couple of weeks later, and that is this one right here, where essentially a user was able to do or take an action, and it impacted pretty much all users of the parity wallet, which ended up locking a lot of funds within contracts, and those funds were no longer accessible. So what happened in this case in particular is, if we look again at this fallback function that they had, the fallback function essentially allowed anyone to make this particular call that would call that kill contract. And so anyone could call delegate call, which could call something else. However, one thing that is pretty well known at this point is when it comes to a proxied contract, you don't want to have any sort of suicide functionality within the upgradable contract or the contract that's being proxied. And that's because if the contract that is being delegated to is destroyed, then all of a sudden your wallet or the contract that you have that is proxying another contract will break. And that's exactly what happened here. So essentially, they had this wallet library contract, and the wallet library contract was not initialized. It was just sitting out in the wild for other people to proxy. However, it still allowed someone to initialize it because it wasn't initialized. They fixed that bug, but they never initialized the proxy contract. And so it allowed a malicious user to go in and initialize the wallet library contract and then to kill it. So that's bad, because once the wallet library contract was killed, like I said, that meant every contract that was proxying that one was effectively killed as well, because now the wallet library contract that they were mirroring was killed. And the functionality that they had to change, like the wallet library, was also killed. And so that meant that essentially what happened here is a malicious user was able to destroy a bunch of people's wallets, and all of those funds were locked in within their wallets, and still are locked within those wallets. So this was a particularly bad case, but is a good illustrator of a denial of service. Yeah. Okay, so let's take a look at a front-running attack. So you guys are probably familiar with front-running, and really what front-running is when someone wants to perform an action, but another user kind of runs in front of them in order to perform this action. It should be noted that front-running is not specific to blockchains. The term front-running actually came from another term from the US stock market, where a stock trader could run in front of another stock trader when they knew a trade that they were going to make, to get their trade in first. And so the term front running is not specific to blockchains, but is illustrative of kind of this central idea where another user has prior knowledge of what some user is going to perform, or an action that another user is going to take, and they decide to take an action because of that, and to get that action posted first. And so in the case of smart contracts or blockchain applications, the reason why this happens is typically because the mempool is public. And so a user can scan the mempool and look for trades or something like that they might want to try to perform first. And then they can essentially pay a higher price for gas in order to incentivize validators to perform their action before other users. So the description that we have for front running is a user executes a transaction with prior knowledge of another user's intentions. And note that in this particular case, I show that the user ends up performing bid before the prior user performs bid. But it doesn't have to be the same action. It just has to be a user using that prior knowledge in order to gain some benefit by performing their action first. So let's take a look at a front-running attack. And this one was kind of difficult to find a good case to illustrate front-running, just because it's kind of just so ubiquitous now in really most smart contract ecosystems. And what I mean by that is you've got MEV bots who are well known to front-run trades that people are making on blockchains. So really, it's not worth reporting the fact that your trade got front run and therefore you lost a bunch of money. And I think one of the best ways to show this is by looking at a piece of code that I got from Solidity by example. It's Solidity by example is used by a lot of people to learn Solidity. And the crazy thing is they have an example of an auction. And in an auction, users are going to be bidding, and at the end, whoever has the highest bid is going to be the one who ends up achieving the benefit. But their bidding function can be easily front-run. And front-running is a very significant vulnerability, particularly for auctions, because if someone is able to front-run any bid, then they can essentially guarantee that they are going to win the auction. And so the fact that Solidity by example or some of these learning materials don't even consider front running when they show examples to users kind of shows how how often this problem is ignored, but there are particular types of applications where you really have to consider front running, because if you don't, then your application is essentially going to be broken. And this bidding example is a prime example of a case where front running really needed to be considered, and they aren't teaching people to actually understand what front running is or understand that they need to consider front running. So in particular, just to show you where the front running vulnerability occurs, front running, or a good way to find front running, is looking for resource contention. And what I mean by that is if there is a particular storage slot or a particular storage variable that multiple users have access to, then you might want to consider looking at or identifying that variable as, potentially allowing someone to effectively front run another user in your application. So in this particular case, because highest bidder and highest bid are both being set by any user that interacts with bid, that means the user who interacts with it first is going to be the one who ends up setting this. And so what a user could do is, if they really want to win an auction, they could just decide, hey, maybe I'll set a cap in order to make sure someone doesn't, maliciously cause me to, bid a significant amount that I can't actually afford. But I'm just going to create a bot, and that bot is going to look for bid transactions. And if there's any bid transaction that's higher than mine, I'm going to front run it to ensure that I have the highest bid. So just to add on to that a little bit, this is specifically malicious because it means that the person who should have submitted that bid didn't get it. And so if there was, so essentially the person who front ran it, wouldn't have to pay the additional fee in order to win the bid. And so most of these auctions have, a minimum increase that needs to, or that a user has to meet in order to actually, outbid someone. And in cases where people don't consider front running, essentially someone could just, ignore that and, make sure that they win. Anyway, so those are the common issues that I wanted to go over. And the thing that I wanted to show here is essentially a breakdown of how often we at Veridise find issues of a particular type. And so the common issues generally fall within all but that first bar. So for example, we went over data validation. As you can see, that's the second highest bar that we have here. Denial of service, access control, front running, and reentrancy. And those are all within the 10 most frequent significant issues that we find at Veridise. So it is definitely worth considering these types of vulnerabilities, because you need to make sure that you're designing your application in such a way that you're not really vulnerable to vulnerabilities that we know about, or that we know can affect particular types of applications. The one thing that we didn't really go over, though, is this highest bar, where at Veridise, the most common type of vulnerability that we find is what we call a logic error. And so a logic error is one of two things, and we are going to look into those next. So at a high level, you can think of a logic error as being kind of an application-specific vulnerability. And so whereas the other vulnerabilities that we looked at were common in that they could, really affect any particular application, application-specific vulnerabilities are either specific to the type of application that's being designed or your specific protocol. And so let's take a look at what some of these applications look like, or what some of these vulnerabilities look like. So the first thing that I'm going to look at is a large stakeholder attack. And so some of you might be wondering, okay, a large stakeholder attack, this sounds like another common vulnerability. For those of you who don't know what a large stakeholder attack is, most other people call it like a flash loan attack. However, I'm not a big fan of that terminology because it doesn't really describe the reason behind the vulnerability. It just describes the vehicle that normally caused the exploit. So what a large stakeholder attack is when a particular user ends up gaining a large stake in a protocol, which can happen through a flash loan, but it can happen through other methods. So for example, another user could gain control over a significant amount of tokens in some other way. So for example, if someone owned like a lending pool, then they could theoretically withdraw tokens that people have put up as collateral and use that collateral in some malicious way, even though they shouldn't. And if you think about it, this is kind of what happens with flash loan protocols anyway. But with a large stakeholder attack, essentially what happens is you've got a single user who is only one stakeholder in the protocol, that because they have so many tokens or so many ways of showing that they are a stakeholder or a significant stakeholder, they can prove to a smart contract, or they can make a smart contract think that a large amount of users want to perform some action. So the way that I describe a large stakeholder attack is when a user gains an outsized influence over a protocol without some financial incentive. So let me show you kind of what this means. So the most famous case of a large stakeholder attack, I would say, is the Beanstalk hack. Some of you might have already, or might already know kind of what happened with the Beanstalk hack, but for some of you that don't, let me describe it really quickly. So essentially, Beanstalk had a particular token which indicated voting shares for the Beanstalk DAO. The way that these voting shares worked is a token corresponded to essentially a vote. They had a way of determining how many votes someone had based off the number of shares, but we'll just, go with that mapping. However, what ended up happening was a lot of users ended up using their, governance token essentially to, lend against or something like that, which meant that someone was able to effectively, get a flash loan for a significant amount of the Beanstalk shares, or the Beanstalk governance shares, and then use those in order to push through a vote. And so more specifically, what happened was someone ended up, putting a proposal to the Beanstalk DAO that said, you should give me all of the money in the Beanstalk DAO. And then because they were able to take out this flash loan of the Beanstalk funds, or the Beanstalk DAO token, they were able to exceed this emergency threshold that was put into the Beanstalk code. And the emergency threshold basically just said, I have a supermajority. I believe that it was set to like 75% of the tokens. And because someone was able to get a flash loan for 75% of the tokens, they were able to exceed this threshold and therefore, just put up a proposal, immediately vote all of their tokens for that proposal, and then execute the proposal all within a single transaction. So the reason why I put this as a logic error is because large stakeholder attacks don't really affect all applications. It's normally specific applications that end up having this particular issue. And what I mean by that is most tokens don't need to really be worried about a single user having a significant share of the tokens. Instead, it's applications that interact with that token need to worry about a significant share, or a user with a significant share of those tokens. And so typically, large stakeholder attacks are somewhat application specific, where you really need to consider them when you have like governance protocols, oracles, because price manipulation, and then we've also oddly enough found them fairly significantly. Well, I guess that's something else. So, but it's kind of specific to certain protocols. And the other thing that kind of indicates to me that this is more of a logic error is because of something that was said by, I believe it was the Beanstalk CEO after this hack, where he basically said he didn't know if he would consider this to be a hack because the protocol worked as intended. There was just a case that was not considered that ended up causing this. So the protocol worked as expected, and can you call that a hack? And to me, that's what kind of signals that this is a logic error, because effectively what someone did is they were able to violate kind of this implicit property that the developers had in mind when they designed the protocol. And in this case, that implicit property was anyone who has a significant share of tokens also has a significant incentive to ensure, whatever is best for the protocol is what happens. And with with flash loans, that's not the case. So that is one type of logic error that we consider, where the developers kind of have this implicit idea in their head about something that should not be violated within their protocol, but it doesn't actually hold. So it's not something that's really specifically wrong with their code. It's kind of something that's wrong with their application, or a corner case of their application that they didn't consider, but they kind of have this implicit assumption about. Another case that we'll look at is this particular case, which is an application-specific attack. And so, in particular, this is an attack that people know to look at when they look at things like proxies. And so with a proxy, you have to worry about storage collisions, because you're using this delegate call, which we already talked about, allows people to modify your state. However, because you now have multiple contracts that are all interacting within the same ledger effectively, they might also overwrite values or the same values within that ledger. So in particular, what might happen is, in this case, you can see that the contract, tells the ledger to write user, and then it reads admin. But if there's a storage collision, they might write to slot 0 when they're writing user, and then they might read from slot 0 when reading admin. And this is because admin and user have collided, and they are living in the same slot. So effectively, what this proxy storage collision is when storage of proxy contracts overlap, which causes some unintended behavior. And so we've already seen a case where proxies can go wrong, and now we're going to look at one other. And this particular case was in a protocol called Audius. I'm not quite sure how to pronounce it. But essentially what happened was they had two contracts. And so they had the proxy contract, and this was the contract that would actually proxy everything else, and then their implementation contract. And their implementation contract inherited from initializable. And what happened was, based off of the default layout that smart contracts have, the proxy admin was stored at slot 0 because it was the first storage variable that was within the proxy contract itself. However, the implementation did not consider the case that it could be proxied. And as a result, what ended up happening was, because there was no offset in where the storage of the implementation contract was going to be placed, it also would, by default, land at slot 0. And so what ended up happening is, here what you can see is, you can see two variables declared. One is initialized and the other one is initializing. And so what ended up happening is, because those two things overlapped, proxy admin would be set, and that would cause these two other variables to implicitly be set. And because the proxy admin ended up being set to a value where initialized and initializing were effectively always true, it allowed someone to be able to always initialize this particular contract. And so it effectively created an access control error where the expectation was, the initialize function should only be called once. But because of this storage collision, what ended up happening was the initialize function was able to be called multiple times by anyone. And as a result, someone was able to effectively take over the contract by initializing the contract again, setting themselves as owner, stealing funds. So this is a case of what we call a logic error, because again, it's something application specific. It's something that we now know to look at for a particular type of application. So in this case, proxies, but it's not necessarily a common vulnerability, because unless you're designing a proxy or something that acts like a proxy, you don't actually need to worry about it. Okay. So now we're going to go and take a look at logic errors in general. So those describe two types of logic errors. One was, essentially there being, a corner case in the design of the application where the developers effectively had a particular behavior in mind that didn't necessarily hold. The next one was application-specific errors, which now we know are kind of ubiquitous and need to be checked when people design a particular application. But this is not specific to those things. It's specific to any protocol. So in particular, a logic error occurs when the protocol implementation does not match the intended specification. And so hopefully you can see why the two previous things that we looked at kind of hit that that description. So the implicit specification of the large stakeholder attack was violated in the case of the large stakeholder attack. And in the case of the storage collision attack, the intended specification of storage slots should be separate was violated. So typically we don't have a concrete specification of protocols, but normally developers have kind of an idea of how the protocol is supposed to work, which hopefully they document. But even in cases that they don't, it's kind of the auditor's job to try to figure out what the intended behavior of the protocol is, to make sure that these kind of explicit or implicit specifications aren't violated. And this is kind of one of the difficulties of being an auditor, but it kind of shows why logic errors are some of the most common types of errors that we catch. It's because a developer had a kind of intention of how the protocol could work, and they either just got it wrong when writing the code, so they just designed their code incorrectly, or they didn't consider corner cases correctly. And so in the example that is shown on this slide, you can see a case where a particular user calls withdraw, and and then the withdrawal function is only reading the balance of the user, but it's never setting the balance of the user. And so this would be a logic error, because you would expect, when someone calls withdraw, it's going to read the balance of the user in order to send funds, but it's also going to write the updated balance of the user to the ledger. So let's take a look at a case where a logic error ended up impacting user funds. So this particular case happened with implementations of a specific ERC. So this was violations of a specification for the ERC 404. And so, exactly what the ERC 404 does doesn't matter. Basically, it was combining an ERC 721 with an ERC 20 in order to create kind of this, fungible and non-fungible token all at the same time. That doesn't exactly matter, though. What matters is essentially this piece of code right here. So what ended up happening is this update function would be called, where the update function was supposed to adjust the balances of from and to. And so effectively update, you can kind of think of as working similar to transfer in your typical ERC 20 contract. However, the problem was, you can see here that in this unchecked block, they set the balances of from, and then they set the balances of to. And in particular, the from balance they get from before that unchecked block, and the to balance they also get before the unchecked block. And so in most cases, this is going to work as someone intends. However, it does not consider the case where from is equal to to. And the reason why I say that is because if from and to are equal, then in those first two lines of code, it's going to get the same balance. So from balance and to balance are both equal to X, let's say. And then when you hit that unchecked box, it's first going to subtract that value from the user. And so it's going to subtract value from X. So value has to be less than X. But then it's going to add the value to the user's prior balance and save that to balances. And so that means that even though temporarily the user's balance was set to X minus value, it ends up being set after the fact to X plus value. And so that meant that someone, by transferring funds to themselves, could effectively just increase their balance arbitrarily, by step of whatever their balance was. So this was a particular logic error, which allowed people to effectively mint funds for themselves when they weren't supposed to, and is an example of a logic error where the actual ERC 404, I'm pretty sure, did not describe things this way, but because the implementation itself did not match the specification, it ended up leading to this logic violation. Okay, so that kind of gives you an idea of the whole graph that I showed you previously. So this graph. So the logic errors that we just talked about, account for that largest particular bar, and then the common vulnerabilities kind of account for the lower bars. And so now, with the time that we have left, I want to briefly go into how do you avoid these errors, or what can you do about them. And so here, obviously one thing that you can do is you can audit your code with an auditing firm like Veridise or many other auditing firms. But you can also use tools in order to try to find these vulnerabilities themselves. And this is something that during the course of, or while auditing, we typically do in order to, augment a manual inspection. So let's take a look at the first thing that people typically do. People typically will write tests in order to find specific types of vulnerabilities. And so essentially with a test, it's very easy to write because it doesn't require any, kind of special framework. There are special frameworks that exist in order to make writing tests easier, but you can do an end-to-end test without needing a special framework. So you have a test. The test is going to execute transactions on the blockchain or a testnet or a local testnet. And then you will check properties after that execution. So the nice thing about tests is they can effectively find pretty much any vulnerability that would be in the smart contract. Note that some vulnerabilities, like reentrancy vulnerabilities, are difficult to find using tests because typically you have to deploy an attack contract. So you have to specifically create an attack contract that can re-enter your contract. But it can theoretically be found with tests. However, it's not necessarily trivial to find reentrancies with tests. But every other application except for, kind of front running can be found with tests. And the only reason why front running can't be found with tests is because normally you're defining, this kind of sequential set of actions that are going to be taken. So it's hard to tell whether something should really be considered a front running attack or if the sequence of your transactions just worked. And, you can kind of model it, but I'm not going to get into that. So tests have the following, kind of pros and cons. So the nice thing about tests is they don't require any specialty knowledge. They can check custom properties, so they can find logic errors. You can define exactly what your protocol should do under certain circumstances. And they don't require custom tooling, even though custom tooling does exist. The cons of tests are they have weak guarantees, and the reason why they have weak guarantees is because you're only exercising your protocol at a specific point, but there can be an issue at a point that you did not test. So you could have an alternate set of inputs that would expose a vulnerability and you just miss them. The other con of tests is they require some sort of user input, and that's just when a user defines a test. However, tests are very important. One thing that studies have shown is protocols are typically stronger when they are both audited, but also well tested. This is because the tests then capture the low-hanging fruit and allow the auditors to look for broader issues rather than effectively debugging the protocol. Okay, the next particular type of thing or tool that I'm going to look at is a fuzzer. And so a fuzzer acts very similar to tests, except effectively what a fuzzer is going to do is it's going to randomly execute a set of transactions on a local testnet. And so it can do so by either just allowing the user to define the inputs to a sequence of transactions, or it can effectively randomly execute transactions with random inputs in order to try to violate a particular specification. So in this case, a specification is still needed which defines do these things, and then check to make sure that this property holds. And yeah, so similar to tests, but normally incorporates more randomness in order to get a broader idea of if there is a vulnerability at more points in the state space. And so because they're very similar to tests and they kind of work more like randomly setting inputs to tests or something like that, they can effectively find very similar issues to tests, where you can kind of theoretically find reentrancies using fuzzers, but again, it requires you creating a smart or an attack contract. And with front running, kind of the same deal, where you can kind of find a front running vulnerability, but it's hard to classify whether it's front running or just intended behavior. So that's why I say front running cannot be found using fuzzing. So the nice thing about fuzzing is, similar to testing, it doesn't require specialty knowledge. It can check custom properties. And the nice thing compared to tests is it can check properties on many inputs. And the thing that's really nice about fuzzing is since it relies so much on randomness, it can generate sequences of transactions or inputs to transactions that developers typically do not check. And so in particular, like many of the vulnerabilities that are found during fuzzing in blockchain applications, but in applications in general, correspond to inputs that the user just wasn't expecting. And this is what's nice about a fuzzer, is it can generate those inputs because it's not necessarily biased towards realistic inputs. The other nice thing is it has stronger guarantees to testing, and that's because testing, you're looking at a particular point, whereas with fuzzing, you're looking at a broader sequence of points, because you're executing effectively the same test on many different inputs, or you're kind of varying the transactions that are executed in order to try to find a violation to a specification. The cons of testing are, again, they only have weak guarantees, because it might be the case that the fuzzer just did not try executing a test on a vulnerable input or a transaction on a vulnerable input, and it still requires some user input, which is the definition of the fuzzing campaign. So some example frameworks for fuzzers are Echidna or Foundry. Orca is the fuzzer that was created by us at Veridise and we use on audits, and Harvey is another fuzzer that was created by Consensus. So the next thing that we're going to look at, and I know we're running out of time, but I only have basically 2 tools left, so it won't take me very much time to go through them, but I will try to go through them very quickly, is static analysis. So effectively what static analysis does is it's going to allow someone to pass their contracts into something called a static analyzer. A static analyzer is effectively going to read the source code and look for vulnerability patterns. And if it finds those vulnerability patterns, it will output where it found those patterns in a set of issues that is delivered to the user. And so the nice thing about a static analyzer is it doesn't require any user input. However, when I say vulnerability pattern, it kind of gives you an idea of what it's looking for. It's just a specific type of vulnerability that someone has to encode in the static analyzer. And so static analyzers can typically find common vulnerabilities like reentrancy vulnerabilities, front-running vulnerabilities, and storage collisions, but they're not as good as finding vulnerabilities that require some amount of customization to a protocol. And so what I mean by this is it's hard for them to detect things like access control violations or data validation problems, because it kind of requires them to know something about the behavior of the protocol in order to say that, this function should be access controlled. And the reason why there are stars here is I'm not saying that they can't do something like this, there are frameworks like zkMonk, which basically perform static analysis, but take in user input in order to define, like, these are the functions that need to be access controlled and protected. And so they theoretically can, but most of them don't. And, same with logic errors. But so the pros of static analysis frameworks are they don't require any user input, or they typically don't require any user input. They typically don't require any specialty user knowledge. If you're using something like zkMonk, then they will require input and knowledge, but most of the static analyzers that people interact with are not zkMonk. And then the nice thing about static analyzers is if they do provide some guarantees, because they basically say, or if they are sound, which they should be, they will say, like, this particular vulnerability pattern does not appear anywhere in your protocol. And so if it's not anywhere in your protocol, then you know that you're at least safe from that vulnerability pattern. So if their pattern is not correct, then that doesn't necessarily mean you're safe from that vulnerability. You also have to kind of reason about what the type of pattern that they're looking for is to say whether that vulnerability is gone or not. But generally, this does provide some nice guarantees when it comes to, looking for specific types of vulnerabilities. The cons of static analyzers are they typically, again, are things like zkMonk. They're not widely used by developers. They typically do not check custom properties, and they can potentially have long runtimes. So static analyzers are usually fairly quick, but for more complicated analyses, they can require a long time to run. So some examples of static analyzers are Slither, which a lot of people are familiar with. At Veridise, we created our own static analyzer, which we call Vanguard, which we use on audits and are working on making public probably next year. And then in Rust, there are also some other static analyzers that are available, like Clippy and Glacier. So the final thing that we're going to look at is formal verification. A lot of you have probably heard of formal verifications, but there are two different varieties that I'm going to go over very quickly. One is interactive theorem proving, and the other one is automated formal verification. So the way formal verification works is the formal verifier will take in your smart contracts and a specification, where the specification defines the intended behavior of the smart contracts, and the formal verifier will check to make sure that the smart contracts are consistent with the specification. Note that this describes automated formal verification. If someone is using an interactive theorem prover, then the user also has to provide a proof, and that proof will prove that the smart contracts are consistent with the specification. So basically, typically they have to prove that the specification implies the smart contracts, and the smart contracts imply the specification. And so interactive theorem proving requires a lot more work than automated formal verification. However, typically automated formal verification has scalability issues, and when it comes to interactive theorem proving, because the user is essentially providing the proof, and the proof doesn't have to be searched for automatically, interactive theorem proving can prove more complex specifications. Also, theoretically, formal verification can prove any particular vulnerability. It just depends on how the model of the verifier. And so if the verifier is sufficiently general enough, it could theoretically find any particular, or it could verify the absence of any particular vulnerability. And so that is nice, but it typically requires a lot of work. So there are some pros and cons to formal verification. The pros are they can check custom properties because the user is providing a specification, and they provide very strong guarantees because if they prove that a specification holds, then it's proven. Not in a ZK sense, it is like proven absolutely, not probabilistically. The cons of formal verification is it typically requires specifications, so a user has to know how to write those specifications. It typically doesn't have termination guarantees, which means there can be potentially long runtimes, and there frequently are long runtimes. And then it also might require specialty knowledge, and this is because with an automated verifier, it could require the user provide invariants or stubs or something like that. And with an interactive theorem prover, the user has to know how to write proofs in that particular language. They also have to know how to translate the smart contract to that particular language if there is not an extractor from like Solidity to Lean or something like that. So some example of formal verification frameworks, so these are interactive theorem provers, are Coq, Lean, and K. So all of them require a user to provide proof or a proof. Some example of formal or automated formal verifiers are, the Certora verifier. So that is fairly automated, where the user does have to provide some stubs and invariants, but generally the Certora verifier is able to prove things more or less alone without much user input other than the specification and those other things that I mentioned. And then at Veridise, we've created a couple of verifiers, but we haven't really maintained those very well. Okay. So an example. But that kind of gives you an overview of the types of tools that are available and also an idea of vulnerabilities and how those vulnerabilities occur in smart contracts.
All right, thank you so much, John. This was super interesting from a development perspective, especially the case studies were so interesting. So thank you so much. We can open it up for a couple minutes. If anyone has questions, feel free to unmute or drop in the chat. I think I see already we have a 3-part question coming through in the chat. Is it okay to have cross-contract reentrants? Might be easier to like.
Right. So is it okay to have a cross-contract entrancy where contract A function 1 calls contract B function 1, which calls contract B function 1, which calls contract A function 2. So it depends on the behavior of contract A and B. So basically what you're describing is a case where, first of all, it looks like you have a recursive call. So it depends on who makes that recursive call. So for example, in the particular case that you're showing, contract B calls itself. And we have seen cases where, that might happen because contract B exposes an external function call and the user decides to immediately call that function again. That can cause issues, but it seems like you're more concerned about the case where contract A function 1 calls some other contract, which eventually calls contract A function 2, which again can expose, kind of this reentrancy, which is still a reentrancy in contract A, because contract A is still in the middle of a call, and control is entering it again. So control doesn't have to enter the same function; it can enter different functions in a particular contract. And we've also seen cases where you might have contract A call contract B, and then contract B eventually calls contract C. And because contract A eventually is supposed to perform some update in contract C, but hasn't done that yet, there's also this cross-contract functionality. And so there's a lot of different ways that these cross-contract vulnerabilities can occur. I hope that answered your question. The next one that you had corresponds to how to allow function access to many valid users not known at deploy time. Okay, so your question is, you want to try to have some sort of whitelist, it seems, where, okay, there's 2 ways that you can go about this. One way is you can define some sort of whitelist in your contract where if users have a way of interacting with like a front end to request access, you can always have the whitelist stored on chain in a contract, which we've had some protocols do, where they've got a contract which just has a whitelist that they update over time. The more common way that users typically allow many users to interact with a contract but try to disallow bad actors is to define some sort of a blacklist where they might interact with another protocol which stores blacklisted addresses. So Chainalysis hosts one of these lists in order to ensure that if someone hacks a protocol. They basically can't send hacked funds into your protocol, and then you have to worry about, how do I extract the hacked funds from my protocol? So this is another way that some people have tried to kind of curb the influence of bad actors over their protocol. Obviously, it doesn't work in general because, you have to assume that a hack has already occurred and someone has updated that blacklist. But in cases where you want to allow your contract to be accessible more generally without having to manage the users more specifically, that's kind of how people do so. Other cases that you could consider, and this is kind of similar to the whitelist, is you could consider where someone goes through some sort of KYC, and then once they go through the KYC, they get whitelisted. That kind of interacts through, or that interaction is very similar to this kind of dynamic whitelist thing that you described, where someone first goes through KYC. Once they go through KYC, then you whitelist them on chain. I hope that kind of answers that question. And then the third question that we have here is, in the front-running example, is a mapping a solution? So I'm assuming that in the front-running example, you're talking about this one. So the solution for this particular case that we have with auctions is not necessarily to have a mapping, because a mapping doesn't necessarily solve the issue, because you have to figure out like who bid first still. And so you still have this dependence on time. And so the way that people typically try to defend against front running for auctions is to instead hide user input. So rather than having a user specify their bid very specifically by doing things like, transferring funds directly to the protocol, or doing something like specifying their bid as the message value. Instead, what you could do is you could allow users to deposit any amount of funds that they want. And then when they bid, what they're going to do is they're going to essentially encrypt their bid. So they're going to take a hash of the bid that they intend to make, and they will post that hash as their bid instead. And then you essentially store the sequence of hashes that end up coming in. And so in that case, because you can't really reverse a hash, they're cryptographically secure, you can hide the amount that someone has bid. So someone can't just front run and say, I'm going to bid the same amount as them, because the hash has now hidden that amount. And so really what happens in that case is you've hidden the amount that people have bid, and you kind of store the sequence that those hashes came in. And then what you can do is you can go through after the auction has taken place, and you kind of collect all of the hashed bids, and you go through what is called a reveal phase. And so in the reveal phase, people basically expose what their bid was, and they either pay the funds that were in their bid, or they those funds are subtracted from the reserve that they posted with the auction earlier. And so in the bid phase, nothing is revealed about their bid because it's cryptographically secure. In the reveal phase, people can't bid. All of the bids have been submitted. And so whoever reveals the highest amount is the winner now. Okay. What was the mitigation for the front running? Okay, I think that was the same question. In general, mitigations for front running can get kind of complicated though, because typically they require you to do something similar to the hiding case that I just described for the auction, where you have to figure out what information someone might front run in order to gain some sort of advantage, and then you have to figure out how to hide that. Hashing is one effective way of hiding that information. But when you have these hashes, you also have to consider some other things like, replay attacks and stuff like that, because, yeah, I didn't talk about replay attacks, but with any sort of hashing or cryptographic proof that you provide, you have to worry about people being able to replay those in contexts where the user wasn't expecting them to be provided. But yeah. Okay, were there any other questions? Not sure if I missed any.
Yeah, it looks like that was going to be my question as well about mitigation for the front running. So thank you. Yeah, anyone else have any last questions? Otherwise, if there's no more questions, I think we can go ahead and wrap for today.
Okay, thanks. And I guess I will see everyone tomorrow.
Yes, thank you very much.
Bye.